I'm Everett Hildebrandt, right there on the screen. I'm from the University of Illinois. Right now I'm working with 2 different companies on formal specification using the K framework. A past project I did was the KEVM, which is the K specification of the EVM. Here I'm going to talk about KWASM, but really, actually, this will be more a talk about K, because I figure most people don't know what K is. And then towards the end, I'll talk about applying it to WASM. So let's dive right in and talk about what K is. And also, if you have questions about K throughout the presentation, I think it's better to ask them early, because then the later slides will make more sense. So this is an overview of my talk. First, the meat of it will be this section 1, Introduction to K, and then I'll talk a bit about KWASM design issues that I've run into while I've been making KWASM, essentially. And then I'll talk about using KWASM and have this pseudo demo thing, which will really just be me clicking through slides. And then I'll talk a little bit about future directions, which will be how to expand this to KeWASM and what other things we can get out of K once we have a fully fleshed out KWASM. Okay. So what is the vision of K? K did not start out as anything to do with blockchains at all. In fact, the main guy leading the K efforts didn't even know what a blockchain was, and it took many meetings of me explaining, well, this happens and then this happens, and consensus is achieved or something like that to him before he even understood it. But basically, it's this idea that programming language tools should be language independent. So, you know, you might make a new language called D or something. Well, D actually exists, and then you can't reuse the debugger that you wrote for C as a debugger for D. Actually, in this case, you could, because D has compatibility with C. But anyway, the point is that you want to write the tools once, and then you want to apply them to all the languages instead of writing a new debugger for every language. So the idea is you separate the development of PL software into 2 tasks. The first task is to develop and to design and develop the actual programming language itself in terms of specifying it. So there you would have a programming language expert who builds the specification of the programming language, gives execution semantics, maybe typing semantics to it, and they don't worry at all about developing tools for the language. They just worry about developing the language itself. And then the second task is all the tooling around a programming language. So you know, these are some common tools that every programming language should have, like a parser. You have to be able to read in programs, an interpreter, a debugger, compiler, a model checker, and a program verifier. I listed these particular tools here because these are all tools K gives you, except for the compiler. That one's in progress. These are all tools K gives you once you have specified the programming language in the K language. So you write down your specification of your programming language in K, and then you get a parser, an interpreter, a debugger, a model checker, and a program verifier out of it. So you can ask me some more questions about that, maybe offline, about those specific tools. But yeah, this is the basic idea. Separate the tooling and the programming language so that every tool you build can be applied to every programming language you build. And here's kind of a picture of this. So there in the center, you have your formal language definition, which is given in terms of syntax and semantics. And then derived, you get all these tools around the side. So let's see if this works. Test case generation and compilers are kind of more in the vision phase right now. Well, compiler is in the in-progress phase, and test case generation is still in the vision phase. Any questions about the K-vision? No? Okay. We have the semantics of many programming languages. I've listed some of them here, but there's many, many more. You can just go to the K Framework GitHub organization and look at, and there's some that aren't maintained by the K Framework GitHub organization, but I mean, realistically, we do the maintenance of a lot of the big ones. So we have C. We've had C for a long time. We use that for detecting undefined behavior, which we've used for verifying code that runs on like ICUs in cars, in modern cars, that you don't want the ICU to have undefined behavior. Otherwise, your car might like just start accelerating or something. In Java, we can detect race conditions. using a tool called Java Mop. So we have the Java semantics, and then we can detect race conditions. EVM we've used to verify smart contracts. LLVM, we have actually done compiler validation from LLVM to x86 because we have the semantics of both, and then we can translate programs between the two, and then we can show they're bisimilar using K. JavaScript, we have found, so we formalized JavaScript, and then, well, I shouldn't say we, it was another member of the team, and he mostly did it alone. But he formalized JavaScript, and he found that the test suite for JavaScript actually didn't test something like 14 features of the spec, and all 14 of those features, the browsers had different implementations, and so we submitted those as bugs essentially, and they got fixed, and tests were added, and the world was a better place. And then P4, I thought maybe some people here would be interested in that one because it's a software-defined networking language where you can kind of lay out how you want data to flow through your network of switches or something. But then we can do data layer verification about whether packets will be delivered or will be dropped or stuff like that. So there's many other languages. Go ahead and take a look at our K framework, GitHub organization to get an idea of all the languages we have semantics for. Okay, so now I'm going to dive into what a K specification looks like to kind of get people warmed up with that. So this is stolen from a programming language called IMP, which we use as kind of a dummy language to show just simple imperative programming language constructs. So you use this extended BNF style grammar. So here we're declaring a new sort called exp, and we're saying that all integers are in sort exp, and we're saying that IDs, which are just like names like A, B, or AB as one string, are also of sort exp. And then we're saying that we can bracket exps with parentheses right here. And we're saying that we can multiply exps and add exps. And notice here, instead of using the bar, we use this caret right there. And the caret makes it so that this operator will bind tighter than this operator. I'll show you an example of what that means here in a second. And then we say, okay, here's a sort statement. And one statement we support is variable assignment. So you can say something like x is set equal to some expression, like 3 times 2 or 3 times y. We can also sequence statements using the semicolon operator. And then you can return an x. So this is just a dummy language. It's not, so far I haven't given it any semantics. And at this point, if this is all you wrote down, all you'd be able to do is parse programs like this. So this would be completely uninterpreted. It would just be parsed correctly, essentially. So A : equals 3 times 2. And then this is an example of this precedence thing. Basically, by using this precedence thing, it will parse this as 2 times A all plus 5 instead of as 2 times A plus 5. And then return B. So simple, that's the parsing part of K. And let's get more into the semantic part instead of just the syntax. So you need to tell K about the structure that your execution runtime kind of has. So in the case of EVM, this structure consists of the network state, it consists of the byte stack, it consists of the local memory, all these sorts of things. In the case of IMP, it just consists of 2 very simple things. We have, well, 3 simple things. The K cell is kind of special. It's included in all K definitions, basically. You don't have to, but by de facto it is. So the K cell will contain the initial parsed program initially, and then throughout execution it'll contain the remainder of the program that's left to execute, basically. So it'll contain the continuation of the program. The environment cell binds variable names to their locations in the store. So you'll say X is located at location 3 in the store. And then the store cell will bind locations in the store to their actual values. So it'll say, the environment will tell you X is located at location 3, and then the store will say location 3 is storing the value 5. So this is, the standard kind of pointer. The environment kind of acts as the pointers, and then the store acts as the actual memory. Okay? And then here we're just telling K, initialize this with an empty map at the beginning of execution, and we're telling K, put the program in this cell at the beginning of execution, wherever you put that $PGM. And actually, program there should say statement, not program. That was a mistake. You tell it the sort. Okay. Okay, so the basis of what you do in K is you define essentially a transition system which executes programs in the programming language that you're looking at. So you just build a model of the programming language as a transition system. So here's two example rules. Here's a variable lookup. So if at the front of the case cell, what you have is a variable of sort ID, and in the environment you have that variable, that same variable, pointing at this store location, and in the store you have that store location pointing at this value, then replace the variable in the case cell with the value. So here we're doing a big complicated pattern matching thing, and it may look like this ... is me eliding details about the rule, but that's actually case syntax. So this is saying, and I don't care what's in the rest. These are called structural frames. I don't care what's in the rest of the environment. I don't care what's in the rest of the store. I don't care what's in the rest of the case cell or what happens after this. I'm just focusing on this part of the case cell, which is right at the beginning. So if at the beginning of the case cell I'm trying to do a variable lookup, do the variable lookup by looking in the environment and then the store for the correct value, and then put the value on the case cell. Replace the variable with the correct value. Does this make sense? Okay. And then variable assignment is kind of the other rule that goes and modifies the store so that you can update, x is now pointed at something else. So if at the front of the case cell I have that x is set equal to some integer, and in the environment I have that x is pointing at this store location, and the store location is currently pointing at v, then replace v with the integer, this integer here, and replace this statement with the empty statement. So we get rid of the statement and we do the replacement in memory, and now the memory's been updated with the correct value. Does this make sense? Okay, so one nice thing here that K lets you do is you can specify multiple rewrites, these are called rewrites, that have to happen at the same time, and it will essentially just kind of pull these rewrites to the top. If we didn't allow that, you would have to write the entire configuration twice with the rewrite arrow between the two configurations, but you can kind of localize where you're doing the rewriting with K, which is one thing that makes writing these specifications a little more compact. Okay, so do these rules make sense? And there's many more rules that go into the imp language definition, and I'm not showing them here, but I'll kind of explain them as they're used in this example reduction I'm about to do. Okay, so we'll start off with this program that I showed before. A is equal to 3 times 2, B is equal to 2 times A plus 5, return B. And this is the initial configuration you'll get. It's not quite accurate. I'm kind of glossing over some things here, but I'm pretending that the environment already has the keys in it. I'm pretending the store already has the memory locations in it. So we're going to say A is stored at memory location 0, which is initialized to 0, and B is at memory location 1, which is initialized to 0 as well. And initially the program is this. So first we look at this rule, this variable assignment rule. So you'll see here that the semicolon is what's separating this first statement from here to here. And in this slide, I've put this symbol right here. That's one of the rules I haven't showed you, but basically it goes through and takes the semicolons and turns them into this K operator, which ships with K, which says essentially focus on this part of the computation and store this one for later, essentially is what this is saying. So we're focused on this A colon equals 6. So A colon equals 6, A becomes this X, well X becomes this A I should say, this integer becomes 6, and then we look up, okay, what is A pointed at? A is pointed at 0. What is 0 pointed at? 0 is pointed at 0, so this V is this 0, and then we update it to I. So the next slide, this will go away because this is saying take it to dot, which is the empty, and this will be 6. And boom, it does. Okay? So that's the execution of that single rule in this particular configuration. Okay? The next thing we do, and once again I've elided some details here, but basically K will tell you there's some other rules that tell it, okay, look at this expression for variables and pull the variables out to the front and put holes where they were so that we can kind of focus in on the variables. So here I've put a hole where that variable was, and I've pulled that variable out to the front. So now we're focused on this variable right here. So here we're saying focus on A, forget about this for a second. And here we look at the variable lookup rule. So A is the variable, and we're going to say, okay, A is pointed at 0 again. That's right there. And then this is telling us, okay, get the value. Now it's at 6. And we're going to replace A with that value, which is what this is saying to do. Boom. A is replaced with that value. And then there's another rule that says once this becomes an integer, take it and put it back in the hole over here. So we do. We put it back in the hole. So now we can actually evaluate this because it's all concrete. So we can actually say, okay, what is 2 times 6 plus 5? And we do that, and then we get b is equal to 17, followed by return b. So does this execution so far make sense? Okay. The next thing we do is, once again, this variable assignment rule. I'm not going to bore you by explaining it all again, but you can see there's the 17, and the b is equal to 17 goes away. And then I'm not going to show the return b because it's not interesting. I just put it there for completeness. Okay, so does k kind of make a little bit of sense here? All right. And we've used this language to build really big programming languages like C and Java, which are huge languages. And here there's only 3 cells in this configuration. The C configuration has something like several hundred cells. I don't remember the exact number. The EVM configuration has over 70 cells. So they get pretty big, and K scales pretty well to these size of programming languages. Okay. So now I'm going to talk about KWASM design, and I'm going to admit that this section's a little less developed because I'm still in pretty early phases of making the KWASM implementation. Here's where the original WASM spec is available at, is at this GitHub. It's fairly unambiguous. I think it's really well written. It's a very good spec, at least better than the yellow paper. And it has this kind of procedural description that you can use to make an implementation, and then it also gives a kind of more formal small step semantics. So because K is a small step semantics framework, it's really easy to just mechanically translate the more formal notation into the K implementation pretty directly. Here's an example rule from the specification. So this is the rule for a loop. So you have a loop. I'm going to actually click this. So you have a loop with these instructions, essentially. And basically, the way that WASM works is you kind of put a label on the stack saying, like, OK, this is what the loop was, and then you execute the loop. And then when you get back to the front of, if you get back to the front of the loop without breaking out of it, then you execute the loop again. So you kind of put these labels on the stack in front of this label right here with the curlies and the end. You kind of put the label in there so that you can kind of remember, oh, this is where you need to go back to once you're done executing this chunk of code. So basically, if you have this loop, it's going to execute the instructions here first, which is just the instructions that came from here. And then once it's done executing these instructions, it's going to jump to this code here, which you notice is the same as this code here. So it's going to re-execute the loop again. And it will only stop executing this loop using this scheme basically if you have a break in there that breaks out of the loop execution. So it breaks out of the labels. OK, so here's that rule again. And now I'm going to show it to you in K. Now, this is all the same information is here, but it's presented a little bit differently because, and I'll discuss this on the next slide, I actually went with a slightly different design decision than the WASM spec did in terms of how to write down these rules, basically. So here's your loop with your type. We don't really have to worry about that. And the instructions right here. And then basically it says, OK, execute those instructions, and then when you're done, if you don't have a break, execute this loop. Here we have our loop, and there's our type, there's our instructions. So loop, type, instructions. And we're going to say, OK, first execute these instructions. So we're saying focus on these instructions first, and then go to the label with the empty type, which is what this 0 here represents as the empty type. And in the curlies, put loop, type, instructions, end. And then here, instead of putting the instructions here, so the thing about the WASM spec is that it mixes the instruction stack with the actual value stack. You can like push values onto it, and then you put instructions on it. And if one of the instructions is like an add instruction, it like consumes the 2 values that are underneath it and produces a new value and puts it on the stack. In the KWASM spec, I actually have separate stacks for the values and the instructions. Specifically, the K cell is the stack for the instructions, and the stack cell is the stack for values. And because of that, I kind of, instead of having this one stack right here, which is like the next instructions to execute in the WASM spec, I separate it out and I say, okay, here's the next instructions to execute, which are just the instructions, and here's the current stack state, which I store off. So it actually ends up, I would argue, making a bunch of the other opcode definitions like break and call a lot cleaner in the K spec than they are in the WASM spec. So I think I'm going to make a pull request. I haven't yet because it's just in the last week did I come across this, but a pull request in the WASM spec may be suggesting this cleanup. But anyway, you can see pretty much all the same information here that you have here, except this spec is executable as opposed to the WASM spec, which is just text on paper. Yeah, and then this is where I'm talking about this 1 or 2 stacks thing. So basically, because you have this stack with values and instructions in it, you have to, when you do a break opcode, you have to search through the stack. Okay, where is the next label that I could break to? So you search to it, and then when you get to that label, it tells you how many values from the stack to keep back. So you have to go back up to the top of the stack, grab those values, and then once again go back down to where that label is and put those values in place at that label. And in the semantics, it has like a whole little section about this this meta-level context operator, just to be able to explain this concisely and compactly. Because in KWASM I'm using these 2 stacks, I can just access both cells directly at the same time, leave the stack intact without having to kind of scroll through it and look for the label. I leave that stack intact, and the instruction stack is what I'm scrolling through, and I can just forget about all the things that I've scrolled through so far. So a little more efficient too. I don't know what the actual interpreter is doing for this, but I assumed it was following the spec pretty closely, but I'm not sure. Either way, the KWASM implementation, I think, is a little bit cleaner than the WASM specification. So I don't know. We'll see. We'll see if it works out. Okay. Another thing that I thought was an interesting design choice is, so I was like, okay, I'm going to make the KWASM semantics, right? So I get the OCaml interpreter and I fire it up and I'm like, okay, I want to push some things onto the stack, right? And I go to push some things onto the stack and it won't let me because you have to define a module first, right? So you define a module that has your function that pushes things onto the stack and does stuff with that. And that all sounds like not really necessary to me. It'd be nice if I could just start pushing things onto the stack and doing operations on it. So the KWASM is kind of designed a little bit more incrementally. So this right here is a valid KWASM program. It can just execute program fragments, which I think is kind of a nice thing for beginners who just want to start playing around with it really quickly. Instead of like the OCaml version, which you have to actually make a valid module and then call a function in the module and then see its effects. I don't know, it's just a little bit. Or there's some online one that I tried as well that also had that problem. So there's another design choice I made. So early stage benefits of KWASM. I've discovered one bug in the spec that I filed and they fixed so far. I have a couple other bugs written down that, well, I think they're bugs. But we'll see what it is. So this is just a benefit of any formalization of anything. You're going to find bugs, basically. I've maybe come up with a clearer presentation of the control flow semantics at this point. I'll have to kind of wait a little bit to make sure that it ends up working with the rest of the semantics being finished. And I have an interpreter now that allows experimenting directly with kind of program fragments instead of having to make an entire valid WASM module at a time. You can just kind of use little program fragments at a time. So these are kind of early stage benefits. All right, so now I'm going to do the pseudo demo. Are there any questions about what I've talked about so far? No? Okay. Okay. So pseudo demo time. These are the steps you would have to take first to be able to do this. You clone the repository, change into the directory, make deps, downloads the correct version of K and builds it for you. Make build will actually take the specification and build the reference interpreter as well as the symbolic execution engine for you. So KWASM is the main runner for KWASM, this little file. So you can do KWASM help and it will tell you all the things you can do. So there's a run command, a debug command. There will eventually be a prove command, but I want to wait until I've proved some things first before offering that. And then there's also a test command, but that's more for my continuous integration testing server, so you probably won't need that. Okay, so this is the program that I'm going to do this little pseudo demo on, the one I showed before. And basically you would just say KWASM run program1.wast. And this is what it would generate. It would say, okay, the K cell is empty, so execution has finished. And the stack ends with a single element of type I32 value 9, which makes sense because you're adding 4 and 5 here. Okay. So pretty straightforward to just KWASM run that. And then maybe KWASM debug would also be interesting to some people because this is really good for when you're developing a semantics and something's not really going how you expect. And you're like, why is it not going how I expect? Well, then you just load it in the debugger, and it will show you the step that things are going wrong at. So KWASM to debug program1.wast. And then it loads up this debugger, this prompt here, and you can say S or step to take one step. And then you can say P or peek to peek at the current state. So the current state is, okay, I'm about to execute this opcode. I've forgotten about this part of the program for now, and the stack is empty. And then we're going to take another step, and we're going to peek again, and it has executed that opcode, and this is the rest of the program right here that it needs to execute. Does that make sense? Okay. And then we're going to take another step and peek, and notice here it took this space operator, which separates opcodes, and turned it into the focus on this part operator. So now we're focused on the 5, and now I'm going to tell it to take 10 steps, and it only actually ends up taking 4 steps until it reaches a final state, which means that no more execution can happen. And that final state is the same final state we got when we did this KWASM run. It's the same final state here that you get here. Does it make sense? Okay, so you get this debugger. I didn't write this debugger. It's just, you know, because we have the C semantics, you can debug C programs now with this debugger. We have the Java semantics, you can debug Java programs. So it's a language-independent debugger. Okay, future directions. I don't know how I'm doing on time. I'm probably a little short. Okay. So that's okay. You guys can get coffee earlier or take a nap. I don't know. So the semantics are really early stage still. Just this week I figured out all the control flow stuff and the issue I was talking about, the 1 stack versus 2 stacks thing earlier. So I think control flow should be largely done at this point, and I have on paper how I'm going to do the frames and local semantics, so that will enable me to do call and return opcodes. There's a couple bitwise operators that haven't been done yet. I haven't done anything floating point because I figure that's not an EWASM, so I don't really need to focus on that at first, and anyone in verification will tell you floating point sex. I haven't done tables, memories, or modules, but I don't foresee those being particularly challenging. They'll just be kind of, you know, grinding it out type of things. And then eventually we want to, you know, take the KWASM semantics and fork KeWASM from that. Really the only difference, as Alex was saying earlier, is that we have this gas metering contract and some other system contracts. So one thing that might be interesting is we could give a direct semantics to gas metering, which is what I think Alex was calling runtime metering before. And if we give that direct semantics and K to gas metering, we might be able to verify that the gas metering contract actually does the same thing as the direct semantics for gas metering, which would be cool because the direct semantics will probably be more human readable, but the gas metering approach is more performant and has other benefits, including being able to run on a normal WASM interpreter instead of having to have a specialized EWASM interpreter. So maybe that's a future direction we could go. That's kind of what I'm leaning towards right now once the WASM spec is done. And then the other future direction is, of course, verification. So right now we have a bunch of verified EVM contracts on this GitHub repo. So runtime verification is the company kind of driving K-framework development, and this is the repository that has a bunch of our verified EVM code. So we'd like to add a bunch of verified KeWASM code as well, or EWASM code as well, to kind of give back to the community, if you will. Okay, so benefits of the K approach, you know, many tools already exist, so you know, you don't have to write a verification engine for your EWASM because we have one. And this verification engine is fairly powerful, and it's automated, it's not an interactive which some people see as a drawback, some as a benefit. So it's up to your perspective. And then also just making an executable specification that's essentially a clone of the WASM specification is clearing up issues with the current WASM specification, which is the same thing that happened when we made KVM, is we found some issues with the yellow paper as well, and we talked to people about them, and we, I think, filed some issues. I'm not sure. Also with like KJS, for example, we found issues with the specification and with the test sets. So. Okay. And that's my talk. Any questions?